Our next speaker is Greg Bowles, who is Head of Government Affairs at Joby Aviation, where he engages key policymakers to expedite introduction of a new generation of air transportation that is safer than driving and so cost-effective it will become a part of our daily lives. For almost 2 decades, Greg has worked in regulation and policy to foster the worldwide safety and success of the aviation community. Before joining Joby, Greg served as VP of Global Innovation and Policy for Gamma, and prior to Gamma, he worked for rotorcraft and airplane manufacturers in advanced design and regulatory roles. Greg holds a Bachelor of Science degree in Aerospace Engineering from Embry-Riddle and a Master of Business Administration from Webster University. He's an active pilot based in DC. Please welcome Greg.
Thank you very much. I appreciate it. And so obviously we're working very closely with Earl and his team, and I think I'll touch on that a bit. Joby Aviation is a company working on electric VTOL. I am not going to unveil anything magic for you today. So one of the inside stories with Joby, for those of you who aren't aware, we haven't really shown much of what's going on with the vehicle, and we will do that eventually. It won't be today. But that's where we are, by the way. That's us in Santa Cruz, California, a beautiful spot. So what I will share with you at a high level, I think you've seen very similar slides from other partners, Uber and others. In fact, I changed this slightly. I had a silhouette of our vehicle for some investors, but I changed it to a logo. So it doesn't look like 8 dots, our vehicle, I can tell you that. You all have seen these slides, but this is the concept. We're working on electric transportation, electric aviation transportation that will be cost effective and time effective, extremely safe. So we really have 3 principles at Joby. The first is safety. So as Earl touched on, safety is the absolute paramount issue here. And we get to safety, to get to true safety, it's actually a little more complex than we like to think as engineers, right? In engineers, as an engineer, I can maximize my area. I've had a lot of roles over my career. Once I was a utility systems engineer working in environmental system design, right? So from that perch, I might have said, I need lots of fresh air exchange. I need backup for flushing smoke out of the cabin. I need a really rigid structure that's going to protect everybody. And if I continue to push and win my way, we'd have a very unsafe design from other aspects, right? So designing a vehicle really takes us the requirement to build it as safe as possible actually requires us to step outside of even our engineering role and look at some of the safety issues. Today, most accidents happen because of pilot error, right? They're stall spins, they're CFIT, they're mismanagement during emergency procedures, which can get pretty complex. And so as engineers, if we say, my job is the reliability of the vehicle, and I'm going to build safety procedures that the pilot will execute, well, humans are really error prone. And if we don't, as engineers, step across that barrier and say, how do I take on some of that baggage that is causing true accidents and pull that into my side as an engineer and solve those more complex interaction issues, then we don't get really any movement of the safety needle. So it's a really important aspect. And when we talk about what level of safety are we building that system to, is it 10 to the minus 9th? It's kind of a misleading argument to go down, because what you're doing is you're actually turning the wrong knob. You're turning a knob that says, I'm going to make something more reliable in an area where I'm not really having a safety issue. Potentially, by making that issue more difficult to certify, I maybe miss the broader integration picture, and maybe I lose some automation that could have solved the problem, because now adding automation is so difficult because I've turned all these knobs so tight that we're going to continue to live with these human error issues that I really shouldn't. So kind of an important philosophy thing to think about as we go forward here. At Joby, here's a slide we haven't shared a whole lot yet, but we've got a pretty serious team of certification staff. So we've hired a lot of really good folks from around the world at this point. We've got an aggregate of 142 years plus of civil aircraft certification experience. Our team has certified over 23 clean sheet type designs, and that's about every one that's happened in the last 20 years. We've pulled all those folks from all over. You can kind of see some of the companies there. But a really great group of folks that have come together to work in active certification through the FAA at this point. So we are stepping into something that's interesting. When the 707, when the 707 was certified, it was a brand new idea, a world-changing vehicle, and the regulations were soft, right? There was not really any rule. There weren't rules for dealing with those things, and nobody worried about it. They made the rules after. They said, okay, what's the right thing to do with this vehicle? Let's do the right thing, and then we'll make the rules grow over time. And that's what happened. We live in a day when it's a mature industry, right? These rules are in place for things like that, and we're trying to bring the new 707 into being, and we've got this whole we've got two problems, right? We've got to accomplish all the technology challenge, and we've got this really difficult regulatory environment that's been formed over the last 50 to 60 years of a really amazing, safe, mature industry. And so how do we do that, right? So when we engage initially with regulators, you go talk to the FAA, and they kind of want to tell you what they've told everyone for 60 years. And it's hard to make somebody want to do something different, right? Luckily, we've got partners at FAA and at EASA and other regulators around the world who are very aware of this issue, and they're trying to figure out how to maneuver in that environment. The difficulty of regulations is you have to meet the regulation or get an exemption. Those are your only two choices, right? You either follow what the regulation says, or if you're not going to, you have to get exempt specifically so you don't have to follow that regulation. A lot of times regulations are written in a vague, broad enough way that you can fit. That's wonderful, because you don't have to go through this big bureaucratic nightmare that Earl was alluding to, the big stacks of paperwork. Sometimes they're not. Sometimes they're super specific, written in a way that they had a totally different framework in mind. You truly aren't going to meet that. You're going to do something completely different, and you need an exemption or a special condition, and that takes time and effort to go through. So when I look at the big issues in my mind, very quickly with the vehicle, we have to talk about design certification. That's where we issue that type certificate for the vehicle. We have to talk about certifying the production of that vehicle. We have to talk about the initial airworthiness, and I'll kind of talk about that subject in a minute. Then we have to talk about airworthiness, so the continued airworthiness, the maintenance, the design changes of the life of that vehicle. And then we have to talk about the operational approval. So it's going to be used for private use or commercial use, and we have to approve those commercial operations. Pilots, if you're unpiloted, that's a whole series of challenges if you're going to try to do autonomy or remote pilot. If you're going to do piloted, what kind of pilot would fly these new kind of vehicles, right? How do you train them? What are the necessary skills? And then we've got a whole lot of air traffic questions, and Earl brought that one up as well. So if we're talking controlled and uncontrolled airspace, what are the rules of the road for these vehicles? Do they have to do something different? Can they follow the existing rules of the road? Where do they fall in the priority of, as I remember, it's less maneuverable vehicles basically have right of way, right? So an aircraft in distress has ultimate right of way, and then a balloon, an airship, a glider, and then common airplanes or helicopters, the vehicle on your right has right of way. So do we follow that scheme, or do we do something entirely different, right? These are the questions on the table. We need to talk air traffic procedures. So a lot of those are geographical. Some of them are published, some are not. There's a very complex world out here that all this stuff that's flying today integrates into. Equipment, comm, nav, surveillance. Do we have to do something entirely different, or can we fit into all this, right? And then you've got infrastructure, municipality issues, local issues, community issues. So the question becomes, do we do something? Are we entirely different? Are we brand new and we have to break all this stuff I just showed you, right? We have to bend everything here? I would say no. I think that's insane, right? So what we have to do is fit into this in the smartest way we can. And over time, just as this system has evolved, it will evolve. If eVTOL becomes a giant new industry that's fitting in well, and there's smarter ways to deal with it, it will evolve, right? And that's where we need to go with this. So that's the question I put on the table. Are we unicorns, right? Are we something magic that nobody knows what to do with? Or are we something else? Like, I throw this in the question, is an eVTOL an airplane? Or, here's an interesting question. Are those both airplanes? Because they look totally different to me, but they're both airplanes, right? And so it's kind of a joke, right? But the question becomes, do we have rules that are flexible enough to deal with the differences between an eVTOL and what other vehicles are? And I believe the answer is yes, because we're right now in a deep certification effort with the FAA. We've had good conversations with EASA. The EASA special conditions are on the table right now, so you can look at those publicly and understand where they are. I will give you a positive and a negative view of that. So my positive view starts with this. The Part 23, CS23 regulations that Earl talked about, those super flexible rules, are the basis of that entire CS23 effort. So they took all of those flexible, high-level rules that rely upon standards and rely upon standards, and they use those in an intelligent way. Then they added a bunch of new things, and almost all those new things are frustrating in some respect. And so I think that EASA has evolved a lot of that to make it more reasonable. FAA is doing something similar. So FAA is working with applicants using basis like Part 23, and then they're adding additional requirements that are reasonable and expected for something that's slightly different. For example, an eVTOL doesn't have the same performance in all aspects as an airplane, right? It has vertical performance capabilities, so you need to take care of that. You need to address do you have 17 knot handling in all azimuths of the wind, right? Do you have crash vectors that take account for some more vertical and forward, not just the forward of an airplane? So these are important things that the FAA is taking into account, using a basis of 23, adding on these special things that are different. The interesting thing about eVTOL is the nature of being all electric means you're very careful with your energy. Hovering burns a lot of energy. I don't know many companies who are trying to transport folks who are hovering, right? These aren't really utility vehicles built for lifting and moving logs or industry. They're meant for moving people, and they basically get on the wing immediately. They spend 95% of their time in true CTOL mode. Some of them do CTOL, take off and land conventionally. And then at the end, you have an option to slow down and come to like a STOL kind of landing, or can even be a zero speed landing, but you really want to get on the ground as quickly as possible. So to me, most of the issues look airplane-ish. They look like an airplane from the perspective of the design, from the perspective, with some differences that we just talked about. They look like that from the perspective of a pilot, the way you fly, and I'll kind of walk through that in a second here, the way you fly many of these vehicles. They look like that from the perspective of air traffic control, right? So air traffic control en route, these things are going to be flying like airplanes. They'll be flying around like airplanes. And then on occasion, they'll want to go to a place that's not a traditional airport, but it'll be a charted location for departing and arriving traffic. Now someday, with great success, that would stress us out. We'd say, there are so many of these things all arriving at this one place. How do we deal with that? That's not the problem on the table today, right? The problem on the table today is, how do we simply integrate these vehicles up into the system like a normal aircraft and back down on the ground like a normal aircraft? So those procedures, right? We have some good ways to separate traffic in uncontrolled areas today. We talk about big aircraft, go to 1,500. Normal GA, hang around 1,000 in the pattern. And if you're really little, go down to 500 in the pattern. We have a common traffic pattern we all understand. We have lots and lots of 5,000 of these airports around the country that we can fly in and out of. We do this pretty well. What happens if this gets really, really dense and we get all this activity? Well, I would surmise that this is dense, guys. We just are doing this week, right? I mean, we're all coming to Fisk and Ripon, and we're channeling ourselves together. That's not relying upon any technology, and we're getting an amazing number of aircraft here. I am shocked every year we do this that we don't have more safety concerns. It's amazing that this works well, but it does. And I'm not saying let's make Oshkosh around the world, right, every day of the week. That's not the point. But the point here is the system flexes to address the needs. And if we have mass numbers of aircraft someday, this will evolve. So it's not a threat today. I believe we can integrate into the existing system in a seamless way without too much risk. So all those challenges I threw on the table, I think are, in the early days, easy to get past. Let me talk through piloting. So this is a really interesting issue. So you're watching a Harrier here hovering during an air show, and this was in the UK. And so there is no aircraft failure there. That's a human error. And what happened was, you can see I highlighted it, the pilot retarded the throttle instead of moving the lift nozzle to the hover stop. And then when the pilot realized that, he advanced the throttle, but he moved the nozzle forward and took away all his lift, and then he dropped, right? So this happened a lot with the Harrier because it was a really complex mechanism to control and hover that aircraft. And back in the early days, as we were discussing in the beginning, the processor that had to do all this work was the pilot's brain, right? What's new here is we have computing power, we have software systems and software abilities to take on a lot of these challenges to make these things more seamless. The very opening conversation I was having, how do we take some of this complexity off the table so that systems can handle some of the complexity, and it lets us humans do what we're really good at, being on the system, right? Watching for things, making our executive decisions. Where should I be going? Is there a storm coming? What's the status of the landing site? Take ourselves to the level where humans are really good at doing things, using our external experiences and thoughts to make smart decisions. And what we're not good at is doing the same thing every day. You can ask my wife, like, I'm not good at doing the dishes. I'm supposed to do that every day, and I often fail. So that aircraft is called the Vok Harrier. It was the derivative experiment that was done between the US and the UK after the earlier Harrier experiences, and it went in to become the F-35B flight control system. So that's called unified flight controls. And the idea here is that instead of transitioning the way that the pilot's flying and does inputs based on phase of flight, it's always the same. So anytime I want to go up, like in an airplane, I pull back and I go up. So if I'm going 100 knots and I pull back, I go up. And if I'm going 0 knots and I pull back, I go up. And if I want to go fast, I push the throttle forward. And if I want to go slow, I bring the throttle back. So a takeoff can look like this, like a normal airplane. Throttle up, some speed I like, 60 knots, I pull back and I climb. Or I decide I don't feel like pushing the throttle today, I pull back. And now I'm going to push the throttle, I'm 30 feet in the air, now I push the throttle forward and I start to speed up. Right? So, and letting go means nothing happens. You continue doing what it's doing. So if I'm in a hover, it sits and hovers. Gust of wind happens, it stays over its point. This is the unified control system that was developed. It's flown in the F-35Bs today. We've started to demo some of this with FAA flight standards folks, and the results have been, we're talking about what is the transition from a traditional pilot to flying something like this? What does it take? And there's no interest in that conversation. Everybody says, that's easy. That's a short little training course. Now, what do we do with people off the street? Like, maybe they can learn this in 2 weeks. Like, this is the FAA folks bringing these conversations up. So everyone wants to go down the path quickly, but I think there are easy early day conversations and then maybe easy middle day conversations. We're actually, just a little teaser here, so GAMA has set up something called the Flight Licensing and Operation Ad Hoc Committee. There's a lot of things GAMA is doing in the space. I'm no longer at GAMA, but I am actually chairing this for them. So on the 21st and 22nd of August in DC, there'll be the first meeting of this activity, and it's to talk through these issues. What do the early days of transition look like for piloted aircraft? So if you were to take commercial pilots, add some delta of training, what do those skills need to be? If you want to go straight to autonomy, what do those parallels need to look like? So the GAMA team is going to build a report that covers the spectrum of things, from transitioning pilots to existing aircraft into these new kind of eVTOL, middle days where you might take someone fresh off the street and give them the knowledge they need just to fly this. And even if you're going straight to autonomy, there are a lot of companies are going straight to autonomy, there'll be a discussion about what that path looks like for simplified vehicle operations into autonomy. So some of my get off stage here conversations will be about noise. I think one of the things we need to talk about is understanding the environment of on-airport noise versus off-airport noise. So today, the on-airport noise construct has been built around the idea that we all look at people who live around airports and we say, they bought a house around an airport, of course it's loud. But we don't let it be too loud, right? If it's too loud, that's not okay. So the threshold the FAA has set is 65 decibels. So if the 65 decibel noise is creeping outside of the airport perimeter, then people get concerned. 65 decibels is pretty quiet. You can kind of see it on the chart there. But at a distance, the FAA tries to constrain that. So one of the things that we're looking at, is that acceptable? So if we were to take that noise threshold off airport and let everyone experience that, people that didn't buy houses at airports, is that acceptable? Probably not. So instead of just looking at a noise threshold, right, a decibel scale threshold, there's a lot of deeper work going on right now. So a lot of eVTOL companies and Uber and other entities are starting to look at loudness. And that's the idea that right now in this room, I'm talking, I have some of your attention. There's a fan going here. I can hear like a blowing fan. I heard some clicking a minute ago over there, but none of that stuff really got our attention because it blends into the background. If a really cool P-51 flew by, we would all say, whoa, let's go look at that. Or if a fire alarm went off, it would catch our attention because we've developed, as humans, we've developed in a way that rapid changes in our environment get our attention, because that's how we stay alive, is by paying attention to those rapid changes in our environment. I'll give you an example. You go to your mother's house and you open the door and you smell chocolate chip cookies and you say, wow, that smells amazing. It's wonderful in here. And about a minute later, you forget about that. It's still there, but it's not a change in your environment anymore, right? It's constant. And so you forgot about it. Same thing with noise. So in the city, if you were to appear in a city all of a sudden, you say it's really, really loud if you had come from the country. But after a little while, the cityscape noise is there. That's the baseline of the noise that we're used to, and it doesn't get our attention. But that's an important concept, because when you come somewhere that's quiet, the noise acceptable level is different. And so what we need to do is understand how these background noises fit in, and how do our noises we introduce change that soundscape. We react to big, quick changes in volume or big, quick changes in pitch over time. A very short time change in pitch or volume. So what's interesting is we all kind of feel the volume thing. If I say something really loud, it gets your attention. But actually a change in pitch that's just as quiet gets your attention as much. So if we had a constant noise and all of a sudden it went very high pitch and low again, it's as annoying as the volume change. So these are really important factors that we're all starting to try to understand better, that we need to pay attention to as we bring these vehicles into the environment. So I think with that, I will say thank you, and we'll talk in a bit. Thank you.